So in this talk, I'm looking at a problem where, in many modern programming languages, comprehension syntax is used to, or is encouraged to be used for writing programs to manipulate large data structures. However, comprehension syntax in executed directly is usually not very efficient. Right? And yet, those programs that you write in comprehension syntax, the function they define almost always have an alternate implementation that is much more efficient. So this represents a kind of what I call an intentional expressive power gap. So the function is there, but the algorithm is not there. So how do you fix this gap? That is the objective of this paper that is published in JFP, and I'm presenting here. So let me give you a example to illustrate what I mean. So in this example, let me use event as a simple data type. So event has a starting point and an ending point and some extra stuff. Okay, and then on event, you can define an ordering, like one event is before the other event if it starts earlier, or if both events start at the same time, then the one that ends earlier is the one that comes before. And we can have different kinds of operations on events. For example, overlapped, two events overlapped in time. Yeah, very simple. So if you look at OV1, the function OV1 is a comprehension syntax. It's very easy to see what it means, right? It's just, if you give me two lists of events, X and Y's, find the X and Y that overlapped. Yes, very straightforward. You understand what it means. OV2 is another function. Probably at a quick glance, or even if you look at it for a while, you do not instantly get what it is doing. But trust me, OV1 and OV2 are actually the same function. They define the same function under the condition that X and Y are sorted according to the ordering is before. Okay, so as long as it is both X and Y are sorted according to is before, the two functions give you back the same answer. And of course, the comprehension syntax OV1 is quadratic. And OV2, surprise, the complexity is linear in the sense that it is size of X plus K times size of Y. K is a number of events that event in Y can overlap in event in X. And typically in real life application, that K is very small relative to the size of X and Y. Okay, so it's effectively linear. That is what I want to talk about today. OV1, comprehension syntax, is very easy, right? You know what it means, but there is no, OV2 exists. It's a function that is much more efficient, but there is so if you are restricted to using only comprehension syntax, it is not, I do not know whether it's obvious to you or not obvious to you, that an efficient function cannot be defined if you are restricted to using only comprehension syntax. And there are many other functions that look like this. For example, this function that you return the pairs of taxpayers, X and Y are taxpayers, and X earn less money, but pay more tax than Y. Or you have two phone models, the price of X is similar to the price of Y. This is a function that you see is very clear. But how to write an efficient program for them is not obvious. Yeah? The reason they are not so obvious is because there is actually no equality test here. If you are equality, you can think of indexing and all this stuff. Okay, but there's no equality. Everything is inequality. So let me come to a first result, which is to show you that actually this intentional gap exists, is real. And I do that in the context of comprehension syntax restricted to a first order setting. Okay, this little mini language is very simple. It just have atomic types, tuples, and simple lists of tuples of atomic types. Okay, and it has essentially the operations for. Let me see. You can construct an empty. Oops, I don't have a pointer. Okay, empty collection, singleton, concatenation of two lists. You can think of that, and then bind or flat map. Okay, so this, as we know, is enough to define comprehension syntax. So this is a little language that basically lets you do everything in comprehension syntax in a very restricted setting. It looks like a toy language, but it's actually enough to encode all flat relational algebraic operation. Okay, so you can do everything your database system can do. The other thing that I need is this concept of Geisman graph. So your input can be very complex, but the input can be represented as a Geisman graph. A Geisman graph is very simple. So the nodes are the atomic values in your input, and then you put an edge between two nodes if these two values appear in the same tuple in the input. Okay, so that's Geisman graph. And because I can have constants and also things inside a list, so I call the constants level 0 atoms, and those things in the list level 1 atoms. Okay, now you can state a very simple theorem like this. If you have any expression in this restricted language, and if this expression has a complexity that is linear, then the following happens. For any edge in the Geisman graph of the output, when you apply this function to an input, then this edge has to either already exist in the Geisman graph of the input, or one end of this edge is a level 0 atom, the other end is a level 1 atoms. It cannot have both ends being level 1. Okay, this is called the limited mixing lemma. It's an intentional counterpart of the locality theorem. So what does it mean? If you cannot have two, you cannot mix. That means you cannot construct two level atoms into the same tuple in the output. So it straight away tells you that, for example, this cannot be done, right? Because two taxpayer will be level 1 atoms in the input list. And you cannot put the x and y together in the output. So this function is not definable efficiently in linear time. Okay, so I have just give you a very quick proof that this intentional expressive power gap is real. So there are things that you can define in comprehension syntax, but you cannot define efficiently. Therefore, we need to fix this gap, right? We all love comprehension syntax, but it doesn't let us program efficiently. So what is missing? What do we need to add, either as additional construct or as a function into our function library, so that you can fill this gap? We don't, this additional thing you add is not something that you want to add arbitrarily so that you can define everything under the sky. So it should not introduce new function, but it lets you define new algorithms. And this missing ingredient, there are several ways to fill it. The way I want to introduce here is synchronized iterations. To define that, I have to introduce some additional concept. The first concept is monotonicity. So basically, it's the is before predicate you've seen earlier. So you have two lists that are sorted in some ordering. The is before is an ordering that bridge these two. Yeah, so you need, if you have two lists, you want to union them together. How do you put them together? So this is the is before. It's represented by a simple monotonicity condition. The more interesting thing is the anti-monotonicity condition. This is applied to the overlap predicate. We call it the canSeepredicate. And it is rather simple. So the first concept is that if, for example, you have this y here, and it cannot see this x, so it doesn't overlap this x, that it would not be able to overlap anything that comes after this first x. Okay, and the other anti-monotonicity condition is that if this y is after this x and cannot overlap this x, then this x will not be overlapped by any y that come after this other y. Okay, so that is the anti-monotonicity. Very simple conditions. And in case this double negation is a bit complicated, you can also flip it around. And what this first one say is, these two conditions say is basically that this can-see predicate or our overlap predicate is right-sided convexity, has a right-sided convexity. What it means is that, for example, if this y can see this x2, then it will be able to see every x between this x2 and this y. Okay, and similarly, if this x2 can be seen by this y1, then all the x that is between this x2 and the y can be seen by this y1. So this is just what anti-monotonicity is saying. Okay, it's right-sided convexity. And what does these two concepts buy us? Suppose your x and y and the can-see predicate and is before predicate satisfy anti-monotonicity and monotonicity, then you can easily write this program. The program is actually the same thing, the OV2 that you've seen earlier, but let me put in it's a bit small, how the anti-monotonicity is used. Okay, so you will see that one case anti-monotonicity condition 1 is used, and the other case condition 2 is used. Maybe it's a bit easier if I explain it in this chart. So if you have, for example, this y1 cannot see this x2, and therefore I know we cannot see everything that come out after this x1. Okay, so what does it mean? If I'm doing a join, an overlap, once I see this condition, y1 is before this x1 and cannot see this x1, I can forget this y1 already, right? Because it will never need to see everything else. It cannot overlap anything else. So the processing for y1 is finished. Okay, I can close it and discard it and move on to my next y2. And similarly, if this y1 is after this x1 and cannot see the x1, then this x1 is not going to be able to overlap this y2. So I can also discard this x1. So this two condition lets me decide when to shift and discard things in my to list. Okay, and that is precisely what these two lines are doing there. All right, so this is what I call the synchrony generator, SyncGen group, and this synchrony generator is efficient. So just to illustrate, OV1 is the over previous query, and OV4 is basically the same query, but now using synchrony generator. Okay, it's very short, and the complexity is again linear if k is very small. So this is what a synchrony generator will buy you. By the way, it is a conservative extension in the sense that you cannot use it to define functions that you could not already define using simple comprehension syntax. Okay, so it does not add any function. It just adds algorithmic power. It just allows you to express more algorithms. So in this sense, it fills that intentional gap. It also has a relationship to database joins. So currently in database systems, joins are implemented by many different algorithms to get efficiency, depending on what that join look like. Okay, purely syntax based. So if your join looks like x dot a equals y dot b is equality, then usually the optimizer in your database system will choose a hash join or merge join or something like that to execute it. And if you have an inequality test, a single inequality test, then your database system will execute it using a merge join. And if you have something like, y is between x plus minus some epsilon, then it is a range join, and a database system will choose a range join algorithm to execute it. And if you have something like y is between x dot a and x dot c, then it becomes a band join, and the band join algorithm will be used. Or if you have something more complicated, like the last one, an interval join, this interval join in database system will usually define a specialized data types like times and all that. Okay, then they will use a specialized interval join algorithms to do that. But more recently, people discovered that actually this can be executed using a union of two band joins. Okay, the difference is that if you use all this specialized algorithm, then for low selectivity, where k is very small, you can get linear time out of them. Okay, but you can see a varieties. But what is very interesting here is that these joins actually satisfy conditions there. So for example, equijoin is convex and reflexive, and the others are all convex and reflexive. Interval join is not convex, but it's anti-monotonic. And I already told you earlier, anti-monotonicity corresponds to right-sided convexity. So of course, if you're convex, you are both left and right-sided convex. So therefore, all of these variety of joins are anti-monotonic. And so they can be executed using Synchrony generator and very efficiently. This is one important thing. And also you can actually rewrite the Synchrony generator in the same form that a database merge join is written. So for those of you who are not familiar with database system, these groups on the left side is a slightly simplified way of writing a database merge join. So it's basically you have two lists, X and Y, that you want to join, and your join predicate is this predicate CS. So basically it says if you process your Y, keep throwing things until you hit a Y that is equal to your X. Okay, at that point you can do the join of X and Y. Yes, and you keep doing this, then until you hit a Y that is different, right? Then you can stop and you can move on to the next X. So that is what the standard merge join is doing. And if you are, but in the Synchrony join on the right side, it is slightly different. First of all, when you process the Y, you would keep the list of things that is Y is before X, and also the list of things that matches your X, that can see your X. Okay, this is the list maybe. Then from this list, you will extract those that meet the condition CS, yeah? Those that you can see. This is the yes, the sublist yes. And no will be all the rest of the Y. And what you return, of course, the join will be your X with the yeses. But the rest of the list is not the no anymore. It's a yes concatenated to the no. Okay, so this is what the Synchrony join is different from the standard merge join. Very small difference. But this small difference is what will buy you the extra general capability, because the traditional merge join requires CS, the join predicate, to be equijoin. Okay? Whereas with that small modification, the CS, the join predicate, is now anti-monotonic. It doesn't have any syntax requirement. It just requires it to be anti-monotonic. So it's a tremendous generalization and simplification in terms of concept and algorithms. Okay, so this is the next part of the paper, because this Synchrony generator is very convenient if you are joining two relations. Now, if you want to join 3, 4, 5 relations, it's syntactically a bit ugly. I didn't quite like it, so I tried to work on how to modify it so that you can get back your comprehension, something as close to comprehension syntax as possible. And it turns out that it is possible to, if you decompose a Synchrony generator into two parts. Now, one part is to convert the initial structure into an iterator, and second is to synchronize, given an X, to synchronize with this iterator to get all the Y's out. Okay, once we decompose it into two parts, and it's quite easy. That short piece of code is a decomposition. So you can also add this Synchrony iterator as a small library function into your standard collection type library. And okay, for those who have access to a compiler and you can modify it. You can even introduce a simple syntax, generator syntax, like this at the top there, and that can be desugared into the Synchrony iterator, like the second piece there. Okay, but once we have this, here is what it will look like. So this program is a simple program to join four different lists: W's, X, Y's, and Z. Okay, 4 different lists. You can think of this as the free time slot of 4 different people, and you want to find a common meeting slot for them. Okay, so the naive program will look like this, and this is how it will look like using Synchrony iterator. So you can see the bottom half. After you create all the iterators, the bottom half is exactly the same as the comprehension syntax. And if you use the syntactic sugar, it becomes like this. Okay, so very close to comprehension syntax, and it is very fast. This is a stress test. So GMQL is actually a very advanced genomic query system to deal with queries on the genome. And queries on the genome, very often you have things that overlap nearby and things like this, and there's no equality test. Okay, so GMQL is very complex, like 20,000 lines of code. When I re-implemented this system using Synchrony iterator, it is like less than 4,000 lines. Okay, and then the performance, this is just one example query. So you can see that on the leftmost chart, the purple bar is original GMQL. The blue bar is when I execute Synchrony iterator in sequential mode, and the green bar is sequential. This is Synchrony iterator executed in sample parallel mode. Okay, so the original GMQL is completely parallel. Not only sample parallel, it also chopped the genome into small pieces and run in parallel. Okay, so you can see the performance is very impressive. Okay, I will stop here. Thank you. Sorry.